Okay, let's continue. So, great. Right. So let me denote. So let I denote the set of sellers, and J denote the buyers. Okay. And I'm going to define the notion of potential. Okay. This is the potential, which always which keeps track of summation of profit for the sellers and buyers. So this is PI plus summation of J is VIJ minus minus PI. Well, sorry. Right. So for the buyer J, I'm going to take the maximum utility. VIJ minus PI. This is the maximum utility for the buyers. Then the initial potential sum will be summation of J from J, max I in I, VIJ. Okay. And my claim is that the potential always decreases. Okay. And that will guarantee the finite termination of this algorithm. Okay. So the reason is that this thing and this thing. So this thing increases by some delta. So the price of the conflict, if we increase the price of each item in the conflict set by delta, it will increase by the number of items in the conflict. And this thing will decreases by delta. So delta is so let me write it down. For suppose that S buyers in a subset S run into a conflict, which means that the number of items that they like the most has a smaller number of items than the number of buyers in the set, which means that N of S is a set of most preferred items, satisfies the number of items in the neighbor is less than the number of buyers. So this is the conflict which will be a perfect matching by Hall's marriage theorem. What we do is we increase each item in this set, increase the price of each item by delta. Okay. Then the profit of sellers will increase because we are increasing the prices of these items. And the total increase is captured by this value, delta times the number of items in the conflict set. But for the buyers, because we are increasing the prices of items, the profit will go down, and the amount goes down by set of S. We use this color. So the total change is delta times n of S minus S. So this is the total change. Plus and we know that the number of items, the number of buyers is larger than the number of items in the neighbor. So this is strictly negative. So we decrease this potential, and the initial potential has a finite value. And every time we update the algorithm, it decreases the potential value. And that is okay. So this is the finite convergence, and I think now the last part is the social welfare. We proved that this is the assignment, the weight of this thing. All right. So for buyers, we know that the total, the final assignment is given by J in J, max I in I, Vij minus Pi. Okay. So we allow the perfect assignment, and each buyer gets the most preferred item after we set the prices accordingly. So let's say this is equal to summation ij final matching, Vij minus Pi. But if you look at this summation, this is ij in M, Pij minus summation of items in Pi. So it doesn't really matter this. So what I mean is that the total profit of buyers is equivalent to the social welfare, because the summation of the prices is just that. So you can maximize the this is the final outcome for buyers, where individual buyers maximize their own benefits, is equivalent to maximizing the total social welfare. That is the idea, because this is a constant term. Well, constant term in the sense that, PI, once you have chosen the prices, people's decision will be to maximize the matching. Any question? Okay, let's move on. So I'm going to talk about two extensions of bipartite matching. So this will be the end of bipartite matching problem for this course. And tomorrow, we're gonna talk briefly about non-bipartite matching, which has, we consider graphs that could potentially have odd cycles, and then we'll move on to something different later. Okay, so let's talk about some extensions. So I'm going to present two variants of bipartite matching. So one is stable matching, and the other one is called the online bipartite matching. And I'm going to explain how they are different from the original one. So let's consider, we get back to the doctor-hospital assignment. So there's a set of medical students who are applying for their medical residency programs, and hospitals basically hire them. Okay? You can think of a bipartite network between these two sets of payers, and we assume that each hospital has just one single position available. Okay? But in practice, one hospital can have multiple positions. So many multiple doctors can be assigned to one hospital. But just to simplify our discussion, we assume that only one position is available for a hospital. So this naturally goes to bipartite matching. Okay. But there's some complex condition that students or doctors and hospitals have their own preferences, and we need to take them into account. So doctors may have preferences depending on locations and salaries and working condition, etc. And also hospitals might want to have some vacancy in certain area, then they have some priorities over certain areas from which they want to hire. Okay. So to explain this thing, we take a bipartite graph, and one set corresponds to doctors and the other side corresponds to hospitals. And individual doctors have a ranking of hospitals. They want to, and also hospitals have their ranking of doctors. Okay. And we want to conform to these preference rankings of hospitals and doctors. Okay, when we want to compute the matching, we basically want to consider these preference rankings of both parties. Okay. This is what we want to do. To formalize what I mean by that, we need to define this notion of unstable pairs. So again, before I define what it is, the goal is to find a stable matching. And a stable matching is a matching that doesn't contain an unstable pair. Okay, that's what we mean. So unstable pair is the following. So let's say there are two doctors U and V and two hospitals A and B. Okay. So we say that the pair of Dr. U and A is unstable if we have the following situation. So Dr. U is assigned to hospital B and Dr. V is assigned to hospital A. Okay. But in fact, U prefers A over B and hospital A itself prefers U over V. Okay. So when we have this situation, there's an incentive for the Dr. U and the hospital A to break their ties and they get assigned to A. And this is an unstable pair. So the goal is to find the matching that avoids, a kind of this kind of unstable pairs in our. Okay. So this is the stable pair. Great. So I'm going to explain one algorithm due to Gale and Shapley. I guess Shapley and another person, the Roth, they got a Nobel Prize out of some work, including this algorithm. Okay, and it's known as the Gale-Shapley algorithm or propose and reject algorithm. And the algorithm is pretty simple. I'm going to explain how it works. So basically, in every time step, doctor can propose to the hospital or applies to the hospital that is at the top of their preference list. Okay. But maybe some hospitals beforehand have already rejected this doctor. Then this doctor ignore that rejected places, and among the available ones, they apply to the top one. Okay. That's what doctors do. And hospitals do the following. So they receive a certain number of applications. Okay. Then they reject because they keep the top candidate. Okay. But they reject all the others one. The hospital can wait until there's a better offer. There's a better candidate coming up. So that is the algorithm. Again, doctors apply to top choices. A hospital can take the top candidate, but later maybe there's another doctor who applies to this same hospital later and has a better potential. Then this hospital can reject this person and replace this by the better candidate. And doctors have to lower their choices depending on whether hospitals reject them or not. This is the propose and reject algorithm. And we repeat this process, and the theorem is that the algorithm always is guaranteed to find a stable matching, or matching that avoids unstable pair. Because this is a kind of intuitive algorithm. Let me give you maybe 2 minutes to think about why it works. Okay. Okay. Maybe let's talk about finite convergence. Okay. So right. So when does the algorithm terminate? So a doctor will stop applying to hospitals if this doctor gets rejected by all their choices. That's the if we run into that situation, we know that we are done. But then a doctor can be rejected. Okay. If no doctor gets rejected, gets rejected, then it means that the algorithm is done. What it means is that hospitals have their candidates, and doctors, because they are not getting rejected, they will stay with the same decisions. So the algorithm doesn't make any changes, so we are done. But then, what is the number of? Okay, and a doctor. So until there's no rejection going on, doctors keep applying. Okay, but a doctor can be rejected order of V times. It can be rejected by all hospitals, and the number of hospitals is at most the number of vertices in this network. Okay. And there are order of V number of doctors. So the total of rejections is order of V squared. And until the algorithm stops, at least one rejection comes up. So the total number of iterations is order of V squared. And now suppose that there is an unstable pair. We have U, V, A, B. I can explain that the algorithm cannot create this kind of situation in words. So, let's say Dr. U. Okay, let me use this. Okay. Dr. U will not apply to hospital B until it gets rejected by hospital A. Because A is in a higher position than B by use preference in use high preference list. Okay. And also, let's say A is assigned to Dr. V, but if you apply to hospital A, then A will replace V by A because A is a better candidate. This, by the design of this algorithm, this unstable pair is not possible. Okay. So for both parties, U and A, again, U will not apply to B before hospital A. Also, A would have rejected Dr. V if it had received application from you. So this is not possible. Question? Okay, I think I will finish quite early for this lecture. Right. So I'm going to give you on another approach based on linear programming. Again, like I said multiple times that for combinatorial optimization there are two different directions. One is purely combinatorial approach, and the other one is based on like linear programming and continuous approach. And this is the second approach for stable matching. So we have this linear programming formulation for maximum weight bipartite matching, right? But if you we want to use this or extend it to so that we can consider this preference ranking of doctors and hospitals. But at this point, this formulation does not have a constraint to impose that condition or the condition to avoid the unstable pairs. So I'm going to write down a constraint to avoid it. Okay. So let's say that I have two edges, E and F. And F, I'm going to say that F precedes E if these two edges satisfy the following condition. So first of all, it could be that there are two situations. So U, V, X, and Y. So U is preferred and X is preferred. So UX, so E is, well, I think, right. E is UI and F is UX. So U prefers X over Y. And F is the connection UX and E is the connection UI. So for you, you would prefer the connection F more than the connection E. Or you have this thing, this F and E. So X prefers U over V. And, so what it means is that, F has a higher priority for hospital X than E. Okay, so this is the natural concept. What it means is that, in other words, we say that F precedes E if F has a higher priority over E. That is. So we write it as this one. So if F precedes E, we use this partial order notation between F and E. So of course, if you take if you take the same edges E and E, E precedes E trivially. It's in 1989, it was observed that you can add the following inequality if you want to avoid an unstable pair. You just write this down. So for every edge E, you enumerate all edges that have higher priorities than E. You add up the corresponding variables. They have to be at least one. So this is the inequality that you want to write down, the avoid. Let's prove that this X is actually valid in the sense that it actually avoids any unstable pair. Okay. So suppose that, this UX is an unstable pair. Okay. Then what it means is you have UX and V and Y such that UI is connected and Vx is connected. Okay, then XUY and XVX is 1. Okay, but UX is not present in your matching. Okay. But in that case, you know, if you collect, okay, let me write it down, UX and VY. Let's say there are like more edges for U that has higher priority than UI, and also let me write down. Let me use different color. And X is connected to edges with higher priorities, but they have all values 0 because you have already used UX, UI, and VX for your matching. But we know that the summation of this thing is at least 1, but these values have value, but the summation of these values has value 0. So if you have an unstable pair, it will violate this condition. In other words, if you impose this inequality in your linear program, then an unstable pair will be avoided. That's what it means. And in fact, on another paper, the same author proved that if you add these inequalities to your bipartite matching formulation, then solving this thing will give you a maximum weight stable matching. So even though this is a linear program, an optimal solution will have 0-1 assignments, and that corresponds to a maximum weight stable matching. Any question? Yeah, so the question is that the number of constraints is V square, which is the number of edges. The question is, can we have a more compact formulation with less smaller number of constraints? I'm not aware of it. I guess for other problems, it's always an open question whether we can get a formulation with a smaller number of data. I think there's a little bit of progress in terms of traveling salesman problem, matching problem, and like spanning tree formulation, but I don't know. I'm not aware of any result about stable matching. I might explain a little bit about that tomorrow for the matching problem. Any other question? Okay, if not, let's move on to our second variant, which is the online bipartite matching. Okay. So the underlying assumption, the basic assumption for our problem, our bipartite matching problem, is that we have access to every part of this bipartite graph. We have all list of vertices and all list of connections and edges. And we look at this global bipartite graph, and like a mediator, like market mediator, looking at all these connections and find an assignment between two parties. But maybe that's not a practical scenario in real world problems. So maybe we have to decide, make decisions of assignment and matching based on some local information about the network. So instead of looking at all parties and all vertices, maybe we have a subset of vertices and subset of edges, and using that information, we just make decisions. But because of the limited information about your network. So let's say I like this problem. So this is called a weapon target assignment. So you can think of weapons as like missiles, and targets are like enemy aircrafts. You can imagine like the missile defense system of Israel. And they are, I guess, like Hamas are sending drones, and the missile defense system launch their weapons to destroy these aircrafts. Okay, but it's not like you have a complete list of enemy aircrafts available. Okay, it's like one drone comes up, and maybe next time another enemy aircraft comes up, and we send a missile to destroy. Maybe this enemy party can do a game or trick, so it kind of sends some useless weapons first, so as to consume all these available kind of high-tech weapons, and then later on they just use the real, like aircrafts, which could potentially damage, give damages to Israel, and at some point, when the missile defense system, exhausted all these kind of available weapons, then this actual, the aircraft can make huge damages on the country. So there's a kind of potentially difficult scenarios going on in this. So again, one side prepares a missile defense system, and the other side launches aircrafts, and it's not like all enemy that arrive at the same time, so they may arrive in an unpredictable sequence. Okay. It's not, you cannot predict what's coming up next. All right, so we have to, when a enemy aircraft comes up, we need to make the decision real time. So if you don't do anything against it, it will create a problem to us. So we need to kind of choose some missile. I mean, it can be expensive or less expensive, but depending on a little bit of prediction about what's coming up later, you choose the proper one to destroy that aircraft. Okay. It's called the online bipartite matching. Okay, where let's say I have two sides of vertices V1 and V2, and V1 is present. It's like I have a list of weapons and missile defense system, but I don't know about the vertices from the other side. So in picture, I have this set V1, but V2, maybe one vertex arrives and another vertex arrives, and later on. But when it comes up later, you have to make a decision for matching. And if you decide not to match this vertex from V2 to one of V1, you have to leave it at that point. Okay. Great. So this explains this word online. So the vertices from the other party arrive online, which means that they come one by one. And whenever it comes, you have to make a decision right away. Let's say if you decide to match this vertex with V1, then you're good. But if you have not decided to match this, then you cannot make the decision later on. Okay. If you decide not to match that vertex to V1, then it should be left unmatched for the entire course of algorithm. Right. So this is what it is. So now we somehow design an algorithm which makes this online decision. So again, when a vertex comes up, you can decide whether it can be matched or not. This is an online algorithm. So algorithm that makes a decision online. And to evaluate the performance of this algorithm, we need to think about how we measure the performance. Okay. Of course, it's not that we have a complete picture of this graph. So our decision is based on local information with limited amount of information. So the quality of our algorithm should be worse than like the augmenting path algorithm, which has access to all the entire structure of this algorithm. But at the same time, I still want to compare what the augmenting path algorithm does and my online algorithm. Okay. That is measured by this notion of comparative ratio. Okay. The comparative ratio is defined as follows. So it's a fraction of two quantities. Its denominator is the maximum size of a match. In fact, we know that it can be achieved by an augmenting path algorithm. And the numerator is the size of a matching that my online algorithm computes. I want to measure this ratio. Its value will be smaller than 1 because, again, my online algorithm has limited access to the graph. So it's the matching computed by this algorithm will have a smaller number of edges than the maximum matching. Okay. And the question is, I still want to achieve a high comparative ratio. Can I prove that it can be at least some constant all the time? Okay. Like an approximation algorithm that we talked about. Okay. So the first algorithm is the greedy algorithm. It's quite simple. So what it is every time a vertex arrives, as long as it has a available neighbor that is unmatched from V1, I make the connection. I leave it unmatched only if there's no available neighbors from V1. Okay, so this is the greedy algorithm. Okay, and in fact, it achieves a 1/2 comparative ratio. Anyone knows a reason why?
어차피 저것도 어떻게 보면 엣지들의 랜덤아이징 시퀀스입니다. 다른 점입니다.
It does have to be randomized in the sense that I guess it can be adversarial. So what I mean is that so like as let's say I'm the enemy and I look at the response of the defense system and I can kind of adversarially adjust the sequence of weapons. It's not something more complicated. It can be more complex than just complete randomness. Yeah.
This becomes a maximal matching.
Right. You're right. So let's go back to slide 1, I think. We have proved this lemma, the theorem on the first day. So for any maximal matching, it doesn't have to be the output of the greedy algorithm, but for any maximal matching, its size is always at least half of the size of the maximum matching. We saw this. Okay. And yeah. Yeah, so we are looking at the unweighted case for online bipartite matching now. Okay. So the theorem just follows that, follows from the fact that the algorithm always finds a maximal matching. This is maximal because if a connection is possible, we add it. And we leave one vertex only if there's only if no connection can be made for that particular vertex. So the output of this greedy algorithm has to be maximal. And then by that theorem, the comparative ratio is 1/2, meaning that the numerator is at least half of the denominator, which is the maximum size of a matching. Okay. Any question? Okay, I guess in theoretical research, maybe in many problems, like even deducing a constant approximation or a constant comparative ratio is a difficult problem. Okay, let's say you have a complex online optimization problem, and let's say my goal is to provide a constant comparative ratio. Okay, let's say you do that. And let's say you write down a paper and submit it to, let's say, NeurIPS. Now you prove that my result improves upon previous results, and it guarantees the best possible comparative ratio. But then a reviewer too who might complain that, oh, this algorithm is too simple, and is there any technical value? And that reviewer can suggest rejection just because the algorithm is simple. Well, this algorithm is good because in the sense that it achieves a pretty good comparative ratio. But maybe the fact, maybe the fact that the algorithm is too simple might not convince the reviewers. Let me give you one more algorithm, which is due to these people, and this is called the ranking algorithm. Okay. So the algorithm is also quite simple, but the analysis is pretty complicated. So let me explain how it works. So for my for the set of vertices that are available to me, one side V1, I randomly assign priorities. For each vertex, I take a random value from 0, 1 uniformly at random. So this is a priority or importance value. Okay. Then based on these random values, you can rank the vertices from one side for that available ones. And what I do is the following. So every time a new vertex from the other side comes up, you look at the neighbors that are available, meaning they are not matched. Then you choose the one with the highest weight, highest priority. Let's say I have X, Y, Z from one side, and I have V here. You look at the available neighbors. Let's say, then now you compare the values of PX, PY, and PZ, and you choose the one with the highest value. So this is a randomized algorithm because this weight and priorities are chosen randomly. But once you decide on these random weights, then the algorithm is deterministic in the sense that you just look at the neighbors and choose the one with the highest value. In fact, then its performance can be measured in expectation because the size of the matching will be a random quantity because your algorithm itself is using randomness. So the algorithm, its performance has to be measured in expectation, and to measure it, we introduce this notion of expected comparative ratio, has to be ratio. So it's just that, in the numerator, we keep the expected size of the matching. Okay. And in fact, you can prove that the comparative ratio, expected comparative ratio is 1 minus 1 over E. And it has value roughly 0.63. But if you look at the analysis, it's quite complicated. So I decided not to cover the analysis here. So this is it for today. Any question? Yeah. Yeah. So right. So how about first of all, I guess when you analyze the performance of a randomized algorithm, not just for like online problem, like determinist, like everything is present, and you look at the offline setting. But any randomized algorithm, its performance is measured in expectation. So I guess your question is about whether measuring the performance in expectation is valid. So that's why I guess people care about getting a deterministic algorithm. So we know that randomized algorithm can do this, but then can you provide a deterministic algorithm without any randomness, with a guarantee that holds with probability 1? Or maybe for some algorithm, you can guarantee that with high probability, with probability like 99%, can you guarantee that your algorithm achieves this one? So, I guess that's a big area. Even like you can de-randomize your randomized algorithm, that like you run some. I guess that this one, when you try to run this algorithm, you use this uniform sampling. Like, can you do some de-randomization technique to use a deterministic one? One way is you run the same algorithm multiple times, and you take the best result. And then how many times do you have to run your algorithm multiple times? If that size is bounded polynomially, then you still get a polynomial time algorithm that works, that guarantees this performance with high probability. So this is one technique to, I guess, go from expected value to high probability value, something like this. I agree with your point that I guess we are looking at this online problem, and maybe this expected guarantee is too weak. Yeah, I guess I don't have an answer for that, but I guess. All right. So the question is about well, I guess, can you prove that the results are concentrated around the expectation? Right. I'm not aware of any result like that, but I think yeah, I might talk about some of my recent results about some machine learning problems, and there I can present the concentration bound, like your statement holds with high probability. So high probability result is about concentration. So your outcome in every situation has to be close to your expected value with high probability. Any other questions? Okay. If not, let's stop here. And I guess tomorrow will be the difficult day of 4 lectures. But okay, so take some rest tonight. And I also need to work hard today to prepare. I'll see you tomorrow. Thanks.